Okay, it looks like we are at 4:10 p.m. Welcome everyone. Christian, are we ready? Terrific. Okay, welcome everyone. My name is Daniel Rodriguez. I am Associate Director of the Institute for Transportation Studies and Professor of City and Regional Planning. Before I introduce our guest today, I want to make sure that you all know that this webinar is being recorded and is being live streamed on Facebook Live. So please make sure you're aware of that. And to provide a better user and a better streaming experience, all the video and audio for everyone has been turned off, of course, except Christian's and mine right now. One important notation: to ask a question of the speaker regarding the content of the seminar for the question and answer session, please use the question and answer feature. That's a little box that says Q&A in this Zoom application for webinars. To contact the seminar support team, because if you have a glitch, for example, or some sort of logistics around the webinar, please use the chat box, but be aware that the chat box between participants has been disabled. So all your chats will come to us to help you with logistics, but all the Q&A for the seminar has to go through the Q&A box on Zoom. So with that out of the way, I am absolutely delighted to introduce our guest today, Christian Claudel, who is an assistant professor of civil, architectural, and environmental engineering at UT Austin. He also has the distinction of being a PhD in electrical engineering from no other than UC Berkeley in 2010. Congratulations. And an MS degree in plasma physics from the École Normale Supérieure de Lyon in 2004. A little bit about Christian: he received the Leon Chua Award for UC Berkeley right when he graduated in 2010 for his work on the mobile millennium traffic monitoring systems. And his interests for research include control and estimation of distributed parameter systems, wireless sensor networks, and UAVs, that is, unmanned aerial vehicles. Christian, the floor is yours. You can take it from there.
Thank you very much for the introduction. And it's my great pleasure to give this virtual seminar today. I hope that everyone is safe, obviously, in these very troubled times. So what I'm going to present today is data assimilation and optimal control in the context of UAV-based flash flood monitoring. And the idea for today's talk is to introduce some high-level control systems that can be used to optimally steer UAVs to maximize the information that they gain when they want to scan flash floods. So I'm going to give a little bit of background on this. But first of all, so this is a joint work with my PhD students. So with Ofer Eldad, who graduated 3 years ago and who worked on the low-level control of the aspect of the system, and with Koen Kian, who is working currently on this system. So Koen is also a graduate of UC Berkeley. He obtained his master's degree in civil engineering at UC Berkeley and is now a PhD student in my group. So he's working on this work that I'm going to present today. So the objective of today's work is to describe what we can do to optimally monitor floods. So floods are obviously a global issue, and you will know that with the increase of global warming, so which is another disaster that is impending, we have actually a lot of flash floods. So flash floods are becoming more present. They are anyway the most common natural disaster worldwide. So in most events actually that are disasters are floods. Floods are really a very important issue, and also they are extremely difficult to monitor because they are very, very fast, very dynamic events. So floods occur really in a very, very short amount of time. They occur on very large spatial scales. They are quite unpredictable because their behavior is highly nonlinear, and it's extremely difficult to monitor them because of this nonlinearity of the model, and because of the very high parameter uncertainty, which is related to the fact that it's very difficult to know essentially how a flood will propagate over a city. And that's because the path information on floods might be irrelevant because cities expand, so of course they build, and what you could predict for a previous flood actually may not apply to the next flood. So fortunately, you can actually sense these floods, so fixed sensor networks are a possible solution. And in fact, there are lots of locations that are already covered with fixed sensor networks. So there are sensor networks that cover rivers, essentially that measure the water levels over time. There are other sensor networks in other locations, for example, in coastal areas that measure the levels of oceans, etc. But it's a very costly solution whenever you want to track floods over extended geographical areas. So this picture represents the city of Jeddah, where I was working a long time ago. And so it shows essentially the scale of the problem. So you see that the city here is pretty large, but actually the floods occur mainly on the mountains far away, and they can sweep the city in a matter of hours. And it's very, very difficult to monitor this extended geographical area of thousands of square kilometers. So you cannot really put sensor networks there. That's way too costly, given the probability of getting a flood. So floods are rare events, and it's very hard to justify that cost. So that's for the introduction. And what I'm going to present now is essentially why we want to do this UAV-based flood monitoring. So a little bit of background on that, and what are the main issues associated with UAV-based flood monitoring. We'll also talk about the next step, which is how can we optimally steer UAVs, which is the prime of high-level control. So given some UAVs that are available to monitor some areas, how do you optimally assign their path and maximize the information that you gain over a short time horizon? So that's another problem with floods. You want to obtain information as fast as possible. You want to maximize the information gain over minutes, because that's the first minutes of the flood event that are the most important. That's where you can decide and organize evacuations or other things that can save the population. And then I will talk about some other activities in my research group. So we are not only doing floods, but that's only part of our research activity. So in the past, I have worked on fixed sensor networks for floods. And this is an example of prototype that I have developed in my research group a few years ago. So that was a sensor network that was actually meant to scan cities. So it's using dual ultrasonic rangefinders, passive infrared arrays to monitor the water level in city streets with a very high accuracy, so with a centimeter accuracy. And the advantage of this system is that it not only scans for floods, but it also scans for a bunch of other things, including traffic, for example, and road condition, as well as other things. So it's really a combination of systems in one, which makes it economically usable on cities. So it's really something that you can use on a city, because you have many other applications that are built in with this sensor. So they can be these type of sensors can be useful for monitoring cities. There are other existing sensors that can be very useful for monitoring rivers as well. So you can monitor rivers, as I said, with radars, for example, or ultrasonic sensors or pressure sensors. So you can still gain some information there. However, one of the biggest issues associated with this type of sensing is that it's very expensive whenever you have very, very large geographical areas to monitor. So it's very important to have real-time data. We have seen that in a few cases where we monitor the floods in cities. So we have seen that, for example, in some cases, you get some floods that sweep across the city. So it happened once on Chaos campus. And there was one drain that was blocked, for example, and so the sensor picked that up because it picked that the water accumulated when it shouldn't. But unless you have real-time sensing, you will always have accidents like this. So you will always have pumps that don't work or things that are clogged. But unless you have sensors, you don't have this information. So that's the value added of sensing. The problem is that this works well in cities because you have a high density of population, so it makes sense economically, but it wouldn't make sense to deploy sensor over very, very large empty areas, even though that might still help a lot because, for example, in the case of some floods, you have floods that develop at the outskirts of the city, and the floods sweep through the city, but you would gain actually so much information if you knew in advance that the flood was coming. And because these things are very rare, there are no instruments that are available to detect the flood. So that's why we are looking for this UAV-based flood monitoring solution. So the idea that we have is to use a set of UAVs for scanning floods. So we use a bunch of fixed-wing UAVs, and the reason for the fixed-wing is that fixed-wing UAVs have a much better range than the rotorcraft counterparts. So for example, if you think of a quadcopter or an hexacopter, so it's very interesting, it's very stable. However, the problem is that it flies for only a few minutes with any significant payload. So it's very, very difficult to use these for scanning floods when you need to cover some extended areas of kilometers or tens of kilometers. So in that case, you will not be able to do any significant coverage if you use this type of sensors. On the contrary, if you use a fixed-wing UAVs, because of the lift-to-drag ratio of the wing, you have actually that ratio actually multiplies the range by a certain factor, and so you have a much larger range. In fact, gasoline-powered UAVs can really loiter for hours over some regions. So that would be very, very useful for floods, when also you have a lot of uncertainties associated with the flood development. For example, you don't know when the high rains will occur. So you have a rough idea from the forecast that you will have some high rains, but you don't know when they will occur or where they will occur exactly. And that's why you want to have some UAVs flying for some hours to make sure that you will cover actually the event. So we would consider fixed-wing UAVs. And then the second problem is, how do we monitor the flood itself? So when you have a flood, you have very high rain rates, you have very low visibility. For example, if you're in a desert, you have a mix of dust that is blown by the wind plus rain, and the flood might happen during the night anyway. So you have actually nothing that you cannot do anything with cameras. Synthetic aperture radars, they could be an option, but their resolution is too low actually to measure the flood. They have only tens of centimeters of resolution, so you need something else. And our idea was to use actually a disposable pingers that would be thrown away. And this is a prototype that we realized a few years ago. So we used simply pingers. So these sensors are not sensing anything. They are just transmitting some fixed ID to the UAV, and the UAV locates them by using some time of flight and the direction of arrival techniques to know the position of the sensor with respect to the UAV. And then from the UAV, you monitor the ensemble motion of these sensors to detect any path or any stream of water that is forming under the UAV. So that's something that can be done relatively easily. So we have seen that for that theoretical problem that we worked on, that was a joint work with Atif Shamim at KAUST, and we have developed actually a sensor solution here that was based on printed circuit on paper. And this sensor is buoyant, it lasts for a few hours. It's degradable. Most of it is degradable except for the battery and the chip, but it's actually having a very, very low footprint. And you can actually make tens of them. They are very light, and you can show them around, bombard some area, and wait until you detect something. So that's the first problem. How do we sense the floods in terms of sensing? The second issue is, how do we control the UAV? So as I said, we would like to use this kind of fixed-wing UAV. So this is the UAV that we are using in the lab, Major Bormatech. And the problem of these fixed-wing UAVs is that even though they have much more range than quadcopters, really they can loiter for tens of minutes, hours, etc., especially if they are gas-powered. The problem is, how now do we manage to control them in very bad weather? This is extremely difficult because when you fly in bad weather, the autopilots are actually very, very crude. So if you look at, for example, a classical Pixhawk autopilot, the only thing that the autopilot will do is basically regulate the altitude and the pitch and roll angles, approximately the path from the waypoints. But it will be unable, for example, to fight a stall or to prevent the UAV from overspeeding or other possible disaster that can happen if you have high wind gusts that shake the UAVs all over the place. So our idea to address that problem was to work, and that was joint work with my former PhD student, Ofer Eldad, that was to develop a flight envelope protection system applicable to UAVs based on machine learning, in which we are relying on machine learning actually to predict the safe set of future input sequences. So that means that, in other words, over a certain time horizon, we are predicting that some sequence of inputs is safe and some other sequence of inputs is not safe based on our current states. And based on this set of future input sequences, so we use an ellipsoid approximation for that set. So that was the best approximation for us in this large dimensional vector space. Based on that, that ellipsoid that can be computed in real time using this machine learning. So the machine learning trains to understand the connection between the current state and that ellipsoid. So we have now then, once this process is trained, we have a computer that is with the UAV itself that will apply this machine learning algorithm to compute in real time what is the shape of that ellipsoid. And then we project the inputs, the current inputs inside that safety ellipsoid, so that we maximize the control authority of the pilot or the autopilot. So that's applicable to both things. But we ensure that actually the UAV doesn't stall, doesn't crash, doesn't overspeed or over-G. We have actually validated this in Austin, in Austin Radio Associates Airfield in 2017, where we flew that UAV. So it's a very slow down video here that you see. On that video, we have actually a bunch of things that happen. So we have this filter that estimates the state of the UAV. So we have actually an unscented Kalman filter that runs at 50 Hertz based on measurements that occur 10 times per second. And based on this unscented Kalman filter, we can actually have the state of the UAV. We then predict this ellipsoid set, which is here. And that ellipsoid set corresponds to the set of input sequences that are safe, that are deemed as safe based on this algorithm. So of course, this process couldn't run on the Pixel autopilot that we used on this UAV. So we had to actually use an Odroid embedded computer to operate that. So if I can replay the video now, and having trouble. Okay, so here it's working back. Now what you can see on this video is that within that ellipsoid set, you have 2 points. You have a red point and a blue point that correspond to the actual position of the actuators, which correspond to the red point, and the blue point correspond to the inputs of the pilots. So you can see that when the pilots try to deviate from that set, so we try to move away. So in that case, we try to stall the airplane doesn't stall, and the system in that UAV actually maintains the pitch angle in the correct angle to ensure that you are having a maximum angle of attack, but you are not stalling. So this is something that is purely based on machine learning, and as well as on the dynamical model of the UAV, obviously, because that was what was required for the training. So the nice thing is that it can really be implemented on real time on a very simple embedded computer. And it's also taking into account the nonlinear dynamics of the UAV. So it's not the same as classical flight envelope protection systems on commercial airplanes that are based simply on the angle limits, for example, or based on actual sensing of angle of attack and then output feedback. So this is for low-level UAV control. Now the next step, which is the third problem that we want to solve, is high-level UAV control, and that's the focus of this talk. So assuming that we have UAVs and we have sensors, which is not a given, again, these things are very experimental work. So assuming that we have now all that, how do we optimally steer, how do we optimally manage our fleet of UAVs to maximize the information that we gain over some time horizon? So for example, here you see the city of Austin. On this map, this is an elevation map. And from this map, given that prior information, given also the expected development of the weather based on the forecast, the radar, etc., how do I release my UAVs in the most optimal way to maximize the information that I will gain over some time horizon? So there are many constraints, obviously. We need to have this information as soon as possible. We need it yesterday, essentially. Because whenever we have a flood, of course, the flood happens on very short time scales, over minutes or tens of minutes. So you want to have the most accurate information as fast as possible to take the right decisions. You have also a bunch of uncertainty. So you have an uncertain prior. You don't know exactly the state of the rivers initially. So you have a good idea, but not exact. You have uncertain model parameters. You don't know, in particular, manning coefficients and a bunch of things that might have changed between floods that happened 20 years ago and the current flood because the city has evolved and more area was built. You have uncertain on the future rain rates, so you know that there will be some rain, but how much or where and when, that's very hard to know. The system is very, very rapidly evolving, and it's also highly nonlinear. So there are some correlation between points that are very far away, but you have to somehow take that into account in your decision for steering the UAV. So this is what I'm going to work on now, which is this UAV path planning problem. So assuming that we are trying to steer this UAV. How should we do this in the best possible way? So first of all, there are many ways to tackle the prime and to think about the prime. So the degree zero of this prime, the first thing is to try to understand how to assimilate the data. So assuming that we have UAVs that show sensors at some location that get measurements, here, based on these measurements, how do I re-estimate the state of the system? So how do I update the state estimate? So this is the objective of recursive estimators like the ensemble Kalman filter, for example, where here we have a state that we estimate at future time steps. So how do I estimate the best estimate of the states at the current step, given my prior estimates and all the information that I have gained in the previous step from the sensors? So that's the classical approach here, ENKF, where we have a certain Kalman gain that is obtained as a function of the state covariance matrices, the covariance matrix of the measurements from the sensors, and also the dynamics of the system, obviously. Now we have also, so this is only for assimilation. So the assimilation step assumes that you know where you're going to place your sensors. The problem is that here, we're not at that point because we still don't even know where we're going to place our sensors. So we have somehow to understand how much information we will gain from our sensors. And there are many ways to do that in the computer science. So the information of a system, you have many ways to evaluate how much information you gain between a prior and a posterior from the distributions of the prior and posterior. So for example, you can use the KL divergence, the alpha divergence, or you can use other metrics based on the covariance matrix here, the log of the determinant of the covariance matrix of the state. Those things are possible ways for you to quantify the information that you have or the information that you have gained on the system. So we need that, and we need also to do another step, which is make the estimation and make the forecast problem as fast as possible. Because when you want to do the estimation or when you want to do the data assimilation, it's not a very, very complicated problem. You take a bunch of ensembles, and then you take some measurement. And that's taking some time, but that's not taking too much time. You can usually do that on regular computers. The problem here is that we are envisioning a scenario in which we have an expanding tree of possibilities where we could place the sensor at different locations, and we have multiple steps ahead, so you can go at certain location and then go at some other location. So of course, the tree expands extremely quickly. And for each of these possibilities, for each story of this scenario where you place the sensor at some locations, you need to somehow assimilate the data and understand how much information you have gained based on a measurement that you haven't obtained yet. So that's furthermore adding additional complexity. So this is something that is extremely complex compared to the simple assimilation or estimation problem. And to mitigate that, what we do is that we use data-driven models in which we replace the partial differential equation that models the propagation of floods by a deep learning model that is extremely fast and that gains actually a lot in terms of computational time. So I'm going to show this a little bit later. But before I show this, let's go back to the problem initially. So we have this problem. So this is the formulation of this problem. So what we try to do here is we try to minimize the cumulative uncertainty over some time with some discount factor under a few constraints. So we have the constraints of the dynamics here of the flood, so the dynamics of the hydrology, that's really related to physics. We have the constraints of the observation. So this is what we have measured based on our actions where we have placed the sensors. Omega, by the way, represents the actions. So it represents where we place our sensors at a certain time step. Now, based on these actions, we have certain observations. We have also certain assimilation that we can do based on these potential virtual observations. And based on this assimilation, we have a certain information gain that we will have, and we will just maximize that information gain or minimize the cumulative uncertainty, which is the same thing. Now, the important point is that also we have some constraints on the actions because the UAVs cannot teleport at different locations. So obviously here we have a constraint that says that the future position of a UAV is based on the reachable set of this UAV at a certain time, so where it can go, given the wind, the constraints, and the dynamics, and so on and so forth. So this is the formulation of the problem. So This is a very complex problem to solve. It's extremely quickly expanding tree, and you can actually solve it by brute force, but it takes actually a lot of time to find an optimal solution for even a very simple scenario. So now, what is the dynamics of our state? The dynamics of the state is driven by the hydrological model, which is here the shallow water equations. The shallow water equations are a very classical model that is used for flooding. It's using 3 states per cell. So if you have a certain location, you will have 3 states. You will have the height of water, and you will have 2 momentums in the x and y direction. If you have a certain set of coordinates x and y, you have this equation that is written above. And you have some inputs. So the inputs of this model are going to be the inflows from the boundaries of your domain, and they are going to be the precipitation. So what is the rain rate function across your domain? You have also some model parameters that are uncertain, as I said previously. So you have the elevation map itself, which is relatively well known usually, but you have friction coefficients, you have runoff coefficients, and these things are very badly known. They actually change a lot. I mean, the range that is given in papers is actually pretty wide usually, so you have a lot of choice for these values. And furthermore, you cannot use the calibration from previous floods usually because cities change, so it's very hard to extrapolate the results of previous floods. So to reduce the computational complexity of that step, which is the data assimilation, remember, if we get back to our problem, we have this step here where we assimilate the data that we obtain from our measurements, which are based on our actions. And to minimize the complexity of that, what we do is that we're going to use a forward model that is going to be based on deep learning. So we replace altogether the shallow water equations by a deep learning based model. So here we use a classical supervised learning in which we have some targets and we try to achieve these targets by training some neural network. And the interesting part of it is that this works actually pretty well if you do the test. So you take, for example, a scenario like the city of Austin, which is this scenario here. You have certain targets, and you have the performance of the neural network, which is pretty similar to the target, so to what we try to achieve with the shallow water equations, but with a time that is considerably less. So it's 3,000 of times faster to use the neural network versus using the shallow water equations. So this really saves a lot of time for this assimilation or for any forecast step for that matter. So that's a very interesting concept that now that will this thing will actually improve a lot the computational complexity of our problem. However, it still won't solve it completely because we have a lot of possible actions here in our problem. So if we get back to our problem, we have this omega of t, which are the possible actions that we are taking. So we have we have actually a lot of actions that can be done on the UAV. So you can see that here, this is the reachable set of the UAV that is encoded by this function. So if you have a fixed wing UAV and if you have a large time steps, the UAV can move quite a bit across the geographical area. So you have actually lots of possibilities for scanning a new point. And furthermore, you can move at other locations. So now you have actually a tree where you have a very large amount of branches, and this grows exponentially very quickly. So that's a very important limitation for this problem. So to address that limitation, what we are going to do in this talk is to approximate this search tree, in which, so in the original search tree, what you should do is you should plan your actions, then get some virtual measurements, perform the assimilations for all of these possible measurements, get some new posterior state estimates, and then rerun the process for all of these virtual new posterior estimates, and so on and so forth, until you march the entire time forward, and you go up to your time horizon, and finally you select the best set of actions that will maximize your information gain or minimize the uncertainty on your system over that horizon with your appropriate discount factors. So that's what you should do theoretically, this original search tree. What we do instead is an approximated search tree in which we are not performing assimilation at every step, but somehow we still need to quantify the information gain that you get after a step. Because when you go at some location and you throw a sensor and you get some information, you cannot just discard that information before you take another decision. Obviously, that information will be very useful to guide your future choice of positions. So that's what we need to incorporate. The proper way of doing that would be to do a full state estimation And once you do this full state estimation, you now have all the new information required to take your next step. The problem is, of course, we said that that takes too much time. So what we do instead is that we replace that data assimilation step by some empirical function of the current state covariance, and that empirical function will represent the information gain that we have obtained over that state. So that's where the heuristics are coming into play to try to obtain a tractable prime out of this original prime. So here now with this said, we are reformulating our prime in which we don't have this original exact prime, but we have an approximated prime in which now the information gain will be quantified by this gamma function here that will pre-multiply this error factor. And this gamma function will represent essentially the information that you have gained based on your action previously. So we have multiple choices for what this gamma function should be. So here we have a possible expression for this gamma function that we are using for this paper. Furthermore, we have to also decide how to take into account the fact that we have some high-level correlations at very, very different locations on our domain. So if you have a certain domain that you need to monitor, you can have actually quite a bit of correlation between different locations that can be very, very remote. So you have to take that into account. And what we do to take that into account is that we create a function that is a decreasing function. And we want to penalize essentially the search over areas that are very highly correlated. So we want to penalize the UAV going from one area and getting some measurements, and then getting to some other area that is highly correlated, that has a state that is highly correlated with the first area. Because when you do that, you gain very, very little information, obviously, because the states are very highly correlated. So here, for this empirical work, we have actually derived a few possible candidates for decreasing functions that we have tested. And with the inverse function, actually, we have results that work relatively well, in the sense that they are very often close to the optimal results that you obtain when you do this brute force search. And that's what we save for the future. So here we have tested on this graph a bunch of possible choices with different parameters and found that this inverse function here in blue is actually consistently giving a high performance and a high reduction in uncertainty compared to the other functions. So these are for the heuristics. Now, these heuristics are very important because they allow us to reduce the computational complexity quite a bit. In the classical prime that we enumerated before, the total computational time for the scenario that we envisioned was 5,400 seconds, and it's reduced by a factor of 50 if now you take this empirical covariance propagation. So you can reduce really by a very, very large factor the computational time, which makes the prime now tractable for a small number of sensors and a small numbers of UAVs. In the previous case, it was completely intractable, even with a single UAV and 2 steps. That's something that is really too complicated. So that allows us at least to get some information and to gain some insight on what, for example, on the case of Austin, would be a right scenario to deploy UAVs and how could we maximize the information over that time horizon. This is the algorithm that corresponds to the choice of actions for a single mobile sensor on top, and for multiple sensors. So we have a slightly different algorithm that now takes the fact that you have joint actions that can be taken by the sensors. So here I'm not going to go too much into details, but that's essentially applying this search tree of possible future actions, computing the rewards for each of the actions, and then finding the actions that maximize the objective function here, which is reducing the uncertainty over that time horizon. So now let's go to a few examples of how we can apply this in practice to simulate the performance of a single or multiple UAVs monitoring some area. So we validate the performance of the approaches in which we are considering 2 path planning algorithms. So we are considering the classical algorithm that I presented now, which is the non-myopic path planning algorithm. So non-myopic because it takes into account what will happen in the future. Whereas we are also considering the myopic algorithm, in which you are just having some greedy approach in which you try to maximize at all steps the information that you gain. And of course, for a UAV, that can be a classical choice. You can say, okay, let's go first to the location that will maximize my information. But if I go there, because of the performance limitation, I may be stuck in some area where I will actually not gain much information after that. So that's where the myopic algorithms can perform poorly in comparison with the algorithms that optimize over a certain horizon that is larger. And you can see that here, if we compare the two types of algorithms, so the myopic is in red, the non-myopic is in blue, you have actually, so of course the estimation errors end up converging to zero, so that makes sense, but you gain quite a bit of information at the initial times with the non-myopic algorithm in comparison to the myopic algorithm. So that's exactly where you need the information. You want as much information as possible initially. So of course, at the end of the flood, you will have a good idea of how the flood has propagated, but these first few steps are the most important for someone that would take decisions. So that's very interesting. And also what you can see is that our uncertainty bars are almost touching here this best case scenario in which, so here in this Monte Carlo curves, what we are looking at is the range of estimation errors that we can get by doing random things between the best case scenario that is the lower envelope and the worst case scenario that is the upper envelope. And you can see that it's quite close to the optimal solution that we could get by a brute force search. Of course, that optimal solution, you can only compute that offline. It will take way too much time to be implemented on. So that's for the first scenario. And you can see also now, if you want to visualize the gains of information, you can look at how much the error decreases as you gain more information. So here in the first case, you look at just the prediction only. So obviously the error doesn't decrease because you don't have sensors to monitor. But if you consider the difference between optimal sensors here that you steer and the randomly chosen paths, you can see that you gain much more information. So here, the darker the color, the more error you're having on the state of the system. And you can see that you have quite a bit of lighter color in the case of mobile sensing with respect to randomly chosen situations. So you gain much more information on the state of the system in comparison to obviously to the case with no sensors, but also to the case where you do actions randomly. So that also validates the idea of optimally finding the trajectories, because that's really something that has a lot of value added based on these tests. So we also evaluated the performance of a single UAV in path planning with a bunch of fixed sensors. And that's something that can happen if you have a river. So in rivers, usually we have sensors that are already there, so we can also take that information into account. And here, that doesn't bring much more complexity to the problem, because when you have sensors that are in reverse, they are already fixed, so they don't bring new information technically. And because they don't bring new information, you can actually use that information very well. So here we evaluated the performance of this situation where you have fixed sensors and mobile sensor together. You can see again the performance of the non-myopic approach with respect to no sensors at all. So here, in that case, you can see the value added of mobile sensing, because you can reduce a lot the uncertainty with respect to just the river sensors. And also the approaches between myopic and non-myopic. Wherever you take a large time horizon, you gain actually much more information than taking actually a greedy approach in optimizing the path of sensors. Right, so let me just move to the next slide. These are some examples of optimal trajectories that you can get for a single UAV with these two approaches. So you can see that the trajectories that are found by greedy algorithms in blue or optimal algorithms in green are very, very different. And you can also see on this map here the difference in the residual error. So here, this corresponds to the real state of the system. And on these two graphs here, you will see just the error level at different points of the watershed. And the error level is encoded by some color map of degrees of blue. So the deeper the color, the more error you're making. So you can see that it's very hard to see on these images, but as you zoom in, you can see that we have quite a bit less residual error in the case where you actually optimally steer the UAV. And finally, you can do multiple UAVs, so you don't have to to do a single UAV or just a single UAV with sensors. You can actually do multiple UAVs. And here you have actually quite a bit of information from having just multiple UAVs versus no information at all. So here, this is no measurement update. That's what you would do if you propagate your prior over time. Obviously, your error doesn't diverge because because the state is bounded, but the error doesn't improve much, while it improves dramatically as soon as you put a few sensors. And also, we have quite a bit more information gained from mobile sensing with respect to fixed sensors, because fixed sensors are at just one location, and once they give us that information, the rest of the information is highly correlated in time, so it doesn't bring much information after that. So now that I have covered this part, so I wanted to cover, that's what I wanted to cover today with respect to flood. So what are the high-level programs in terms of sensors, UAV control, high-level and low-level control. So I focused mainly on high-level control for this talk, but as you have seen previously, this is really a problem that is far away from being solved, given that you need to actually solve a bunch of things on the sensor side and the low-level control side of things. I would like also to discuss a few other research activities that we have in the research group. So the mobile sensor lab at UT Austin, so that's called the MASS lab, Mobile Automation and Sensing Systems. So some of the activities are dealing with optimal control in roadway networks, which was my original work at UC Berkeley as well. So here we're interested in this work with Suyash Vishnoi, one of my PhD students. We are interested in computing the optimal policy for steering cars on the road. So sorry, not for steering cars, but for controlling the speed limits on the highway network to maximize the throughput of a highway network. So we have a certain road network here, which is around Austin. So that's the I-35 road network. And we have a certain simulation, which we have some states that are known. And here we compare the performance of two algorithms, including the one that we have developed on the right, which clears the congestion faster than the classical algorithms used on the left. So it is based on a mixed integer linear programming formulation of the LWR traffic flow optimization problem that we have developed in the past. The difficulty here is that, of course, we have to optimize some model parameters instead of optimizing over the states or over the inputs. So that's quite a bit more complicated conceptually, but that still results in a mixed integer linear program, and that allows us to get an optimal solution that is exact as well. So if you solve that MILP, you get the optimal choice of dynamic speed limits as well as boundary control actions on the on-ramps to minimize the congestion over some highway. We are also working on other research work on highways as well. So one of the other activities is to do some boundary control on highways. And for that, with a PhD student, so with Hao at UT Austin, and Randy McNair, a colleague at UT, we have worked on some algorithm that can be used to maximize the flow across a road network, but now taking into account the uncertainty in the parameters. So here, when we optimally allocate flows, usually in traffic, one of the big things that we forget is that we have a lot of parameter uncertainty. So when we try to maximize the flow, we might actually do a worse job by allocating the optimal flows, because simply we have so much uncertainty in the state's evolution that we might actually do worse than no control at all. Here in this case, what we're interested in is actually using the uncertainty that we have on the turning ratios. So the turning ratios are important parameters on road networks. They are telling you how much percentage splits over one road with respect to the next road. And this is very poorly known. Usually it changes over time as well. So what we are interested in is to optimize the flow here, but with a robust optimization approach in which we are trying to take into account this uncertainty in the turning ratios, and that results in a SOCP, and that SOCP can be implemented, and it can yield results that are very fast. So of course you get chance constraint optimization, in which you have some tuning parameter that represents your aversion to risk, and based on that you can see that here in that case, if you put some uncertainty on a certain node, you will have the corresponding on-ramps that will have a certain uncertain flow as well, because you don't know exactly how much capacity is left, so you will have to adjust the flow accordingly. And similarly in the other example. So this was just to show qualitatively that we could achieve these results. We are also working on other activities related to CPS, and so this is a project funded by the NSF CPS. The objective of this project is to use augmented reality glasses to improve the throughput of intersections when we have purely controlled intersections. So imagine that you have a future world of autonomous vehicles that go all over the place at very high speed. You can imagine that they would approach the intersection and they would go through the intersection extremely fast without using traffic signals. They would coordinate perfectly and not collide, obviously, and get through the intersection in almost no time, which would increase the throughput of the intersections, which are major bottlenecks in cities, and therefore you could travel on the city very quickly without any congestion. So that's for the theory. In practice, we know that autonomous vehicles will not arrive at once, and we won't have 100% autonomy. And in fact, when you look at these schemes for allocating flows across intersections, these schemes work very well if you have 100% automation, but as soon as you have even 1% of non-autonomous vehicles, the benefits completely collapse. So that's a major hurdle, because we know that it will take tens of years for autonomous vehicles to generalize and to be working properly. And so what we wanted to do here is to try to see how we could use augmented reality to give information to users to go through the intersection safely. And so here, this is a joint, so this is a prime that is at the intersection of control and human in the loop control as well. So we need to have some human factors consideration, obviously. You have some virtual car that is written in, that is drawn in wireframe in your field of view, and you have to follow that virtual car. And we have to evaluate what is the performance of humans in that low-level tracking activity. And based on that performance, we can allocate some time slots. So of course, it's a competing objective of safety, between safety and capacity of intersection, that we have to work with. So we have people that are working in human factors, as well as the computer science side of things, and also colleagues at UT that are working, for example, on the optimal placement of these future intersections to maximize information gain. On our side, we have worked with Koen and Abdullah on the project that was meant at detecting and forecasting the future paths of users here. So if we have people that are walking on the streets with these goggles, how can we know what will be their future paths if they are not controlled? So if they don't wear any goggles and we just see them, what will be their future reactions? That's very important for the system, because the more you know about the uncontrolled people, the better you will act, and the more safely you will be, the more safe you will be. So we have submitted this paper. It was accepted at CVPR this year. And now we are working to extend that concept of uncontrolled users to evaluating the performance of controlled users. And again, based on deep learning algorithms. So here it's a combination of deep learning and graph theoretic models to evaluate what will be the performance of users that have to do some task. And based on that performance that is dependent, that is user dependent, how can we allocate flows on intersections to maximize throughput while being safe? And finally, some other activities. So here, this was canceled this year. Probably Elon Musk had visions of a pandemic. I'm not sure if it's a possibility, but we have been working on the past few years on the Hyperloop for the SpaceX competition every year. And in particular, we have worked on this pod here called Furiosa that is based on air bearings. So I know that UC Berkeley also has a team. And this is some very interesting activity. I hope that all this will continue later on, but that looks like a very interesting and promising transportation system in the future. So this concludes my talk for today. Just to give a brief overview of what I mentioned today. So we introduced a path planning algorithm for mobile sensing of flash floods. This algorithm is based on the minimization of residual uncertainty over some time horizon, but we cannot solve this because it's taking too much time. Even for small-scale programs. So what we worked on was to use some heuristics to quantify the information gain over some time horizon, and then incorporate these heuristics and solve the corresponding program to find the optimal path. So we showed a few examples of how much information we could gain from these UAVs with respect to fixed sensor networks, and also why we should consider these certain time horizons in the future, with respect to just the greedy algorithms that would lead to poor performance. In future work, my PhD student Koen and I are going to work on the decentralized path planning algorithms to distribute these computational requirements among nodes and hopefully be faster. If you can imagine now that you have several UAVs, you could actually probably gain more information by distributing the load here. And then we will investigate also the path planning problem. So how can we now consider the same type of problems, but on larger dimensional systems? So for example, if we want to monitor a lake, we have already a robot, AU, so we have an underwater robot that can monitor Lake Travis. And obviously we cannot use it right now, but we want also to track, for example, contaminants or microplastics in lakes. And that's a very interesting assimilation problem because it's now a 3D system. So you have more states, obviously. You have one dimension more, and you have similarly some very complex dynamics that can happen. Furthermore, you have to also estimate the states of the system at the same time as the parameters of the system, because you have the flow patterns that are unknown as well. So this is also some very interesting and challenging problem. All right, so I will stop the lecture. I will start the presentation here, and I'm happy to answer any question you may have.
Wonderful, Christian. Thank you very much for a comprehensive presentation. That was very exciting to see and to get a sense of your broader research effort. So I want to encourage those in the audience to go ahead and ask questions. Please submit them through the Q&A box. But I wanted to maybe begin with a fairly basic question. So let me lead with this. And it is whether the performance of your proposed approach is influenced by the characteristics of the flooding area. In other words, whether the complexity of the features in the study area, for example, if it's an urban area with buildings, fields, human-made lakes, creeks, trees, roadsides, versus a riverbank being flooded, impacts the performance of your approach.
Yes, so thanks. That's a very interesting question. So I would say theoretically no, but I don't have much. I mean, I don't have the proof for that. So if you look at the algorithm itself, the assimilation process is based on this data-driven model here that we are using. So if I go back to that corresponding slide, this is the deep learning model that we have trained. So we have trained that model only for Austin watershed. And obviously, if you train it for some other locations, you might get a different performance. We found that on the Austin watershed, the performance was pretty good. And that's where you save hundreds or thousands of times in terms of, I mean, you are hundreds or thousands of times faster with respect to the classical shallow water equation implemented on the same computer. That said, this is for that particular watershed. So I'm not sure if these results generalize to any other situation. We believe that there are enough features in this, but there are some caveats. For example, for very flat cities that are flooded, where you have a very high complexity in the flows, where you have really very complex, high two-dimensional flows, for example, we are not sure that this data-driven model might have the same performance. So it will all be driven by this type of model there.
Mm-hmm. Great. Thank you very much. Let me jump in and read a question that Scott Mora has asked. I'm examining a sensor placement problem myself, and we have struggled with metrics for observability. Observability analysis, as you know, yields a binary conclusion, observable versus not observable. And I'm intrigued by the concept of information gain because it's continuous, and as you showed, you can optimize it. Can you talk about the relationship between information gain and observability?
Yeah, that's a very interesting question. Again, completely unanticipated. It's definitely, this is really a very, I mean, that's a very critical difference between observability and, as you say, observability is really an on-off concept. And, this is really, I'm mainly aware of observability in the context of linear systems. So I'm not extremely familiar with observability for nonlinear systems, but definitely you cannot optimize much observability for nonlinear systems because you are either or not. For the case that we are dealing with here, we wanted to focus mainly on on the information gain because the most important factor for us was to reduce the uncertainty, and again you can also modify this thing. Here we wanted to modify to optimize over the overall uncertainty of the system. In practice, you could actually modify that approach, the objective function, to, for example, minimize the average uncertainty over the areas that are the most critical in your system, because that's where you would have the most impactful decisions if you have to manage these locations. But definitely for the approach of probabilities, I mean, it's very interesting. We haven't used that approach at all, so I'm not really able to comment much on what we could do on that standpoint. We went immediately to the concept of information gain, and again there are many possible information gains that you can think of. So here we are basing things based on the uncertainty of the system based on the log of the determinant of the covariance matrix, which is a possible metric. But there are many other metrics that you can use, which we haven't investigated here, and that could also give some information as well. So because of this variability of metrics, it's also very difficult to understand what is the impact of one metric versus another in solving the optimization problem.
Great, thank you, Christian. Any other questions? Jump in. I do have one. Amanda, you want to go ahead and answer your question? Ask your question, please. Maybe I'm misreading the chat. I don't know what the chat was saying, but I will jump into with my question. And I was thinking about a city in the global south that is facing one of these flooding hazards. Can you use your approach, Christian, to determine the optimal number of vehicles to deploy vis-a-vis, for example, cost, area to be scanned, other trade-offs to provide the services that the city might want to have, for example, keeping surveillance and an eye on flooding? Is this type of optimization and kind of advice for, as a city planner, it comes into my mind. Is it available and feasible to provide?
I think that would be feasible. So as we see currently with this pandemic, we see that, you know, the extreme, I mean, in the spectrum of possibilities, you always have extreme cases, and if you want to be robust against the complete set of cases, you can be extremely conservative, or you can, I mean, of course, you can optimize over that. I would say that one of the major difficulties when you want to do this is really the unpredictability of flood patterns. Even there can be some flood patterns that are highly predictable. For example, coastal floods can be quite predicted quite well, or if you have a flood that is due to a tsunami, that would be well predicted. If you have a recurrent floods related to rainfalls, in some situations the floods can be predicted very well. So it all would depend on the predictability of floods versus also the risk averseness of the people that operate the city, because even if you have predictable floods that occur once in a while, you always have a 100 years flood or a 500 years flood, or etc., and so on and so forth. And depending on how conservative you would need possibly more sensors, and depending on the patterns. So I would say it's really something that you can possibly solve with this algorithm. You can probably quantify how much information you gain, and you have to, of course, optimize. You have to optimize over a variety of choices of priors and of scenarios of high rains that you can take maybe from historical data. And if you optimize over that, you can probably, given a certain information gain that you would get over a certain reasonable time horizon, you can try to quantify how many sensors you would need to achieve that. But I think it's a very complex issue because of the complexity of the nonlinearity, of the difficulty of estimating the coefficients and the parameters right. And I mean, for example, one thing that we see often is that after a flood, we can really repredict what was the flood pattern, but just before the flood, because we didn't have the Manning coefficients and all these coefficients parameterized and known, it's much more difficult. So I would say that's a possibility with this algorithm. You can probably do some, I mean, apply this algorithm to a set of priors to estimate
Great. Thank you, Christian. That's a very helpful answer. I know that we are over our allotted time by a few minutes. I wanted to thank you, Christian, for telling us about your research. It was very interesting. Thank you to the audience for joining us. And please be on the lookout for another announcement of a seminar that we're going to have this semester. In the meantime, everyone, please stay safe, have an enjoyable weekend, and we will be in touch in the near future. Christian, our thanks and gratefulness for your time. Thank you. Bye-bye.
Thank you very much. Have a great day. Thanks. Bye-bye.